Hey guys, welcome. Yeah, so while I will provide you an additional at least 3 examples working through problems applying Cauchy's theorem for contour integration, here in this video, as with all example zeros, we're going to do the most exciting thing, which is prove the theorem. So we're going to prove Cauchy's theorem here in this video, yeah? Okay, cool. So let's first state it. What Cauchy's theorem says is that if f is analytic in a simply connected domain D, then along a simple closed contour C and D, the integral over the simple closed contour C of f of z dz is equal to 0. That's what Cauchy's theorem says. And this is a very powerful result, as you will see in examples 1, 2, and 3. And there may be more examples in the future, yeah? Okay, cool. But yeah, why is this true? Let's prove it. So the proof heavily relies on Green's theorem and also on an assumption that f prime of z is continuous. So in this proof, we assume that f prime of z is continuous. Now, this theorem is proven to still be true without the assumption that f prime of z is continuous, and that is due to a mathematician who continued working on Cauchy's theorem by the name of Gorsa. So I think that's how you say it. I know a little bit of French, but anyway, that proof without the assumption that f prime of z is continuous has the name Cauchy-Gorsa theorem, but it's saying the same thing that this theorem is saying. Yeah, okay, cool. All right, so without the requirement that f prime of z be continuous. But here we assume that f prime of z is continuous, and then we know by the definition of what we mean by the integral over c of f of z dz, we can say that f of z first is equal to, by the way, I have a video dedicated to defining what we mean by the integral over a contour of f of z dz, so check out that video. But yeah, we're going to do in this little part what we did there, which is like we're going to say that f of z is some complex number u plus I times v, right? So f of z is u plus I times v. Now, f of z, the output, is a complex number that has a real part and an imaginary part, but the input z is also a complex number, so z also has a real part and an imaginary part, and the real part of z is x, and the imaginary part of z is y, and therefore z is x plus I times y. And so what I'm saying is, I'm writing this, what we're saying is f of z, and therefore f of x plus iy is equal to u plus iv. So let's make note of that, because it's important to know that like u plus iv is not z, it's f of z. Z is x plus iy, right? And it is for this reason, because z is x plus iy, that we have the dz is equal to dx plus I times dy. Okay, so then this integral here has us multiply f of z and dz. So what we're going to do is we're going to multiply u plus iv to dx plus I times dy, because that's f of z dz. And if we do, then we can say that this here is equal to this right hand side. And that's because like after you multiply u plus iv and dx plus I dy, if you collect the real part, you'll get this. And if you collect the imaginary part with the I factored out right there, then you'll get this. And so then this integral now becomes these two integrals. And that's fairly straightforward. Like I said, there's a whole video dedicated to talking about what we mean by integration for complex functions over a contour. And so watch that video if you need reinforcement on what I just did, but it's pretty straightforward. Okay, cool. Now we make use of the assumption that f prime of z is continuous. What that means is that u and v have continuous partial derivatives. And it is because of this that we are able to apply Green's theorem. Like I said, this proof of Cauchy's theorem heavily relies on Green's theorem, other than this assumption here earlier, right? Okay. Now, so from f prime of z continuous, we get that u and v have continuous partial derivatives, and so Green's theorem applies. Now, what did Green's theorem say? So let's remind ourselves. But let's also remind ourselves of where we left off, which is right here, yeah? Now, what Green's theorem says is this, which is it takes a line integral and turns it into a double integral. And Green's theorem is something that you first encounter late on in multivariable calculus, aka Calc 3. But yeah, here's a statement of Green's theorem. So you have this line integral and it turns into this double integral, yeah? So what we're going to do is we're going to apply Green's theorem here on this line integral and this line integral. Now, pay attention on this line integral, this v here, which in Green's theorem is positive, is negative here, yeah? So what that means is that when we turn this line integral to this double integral, the dv dx, because v is negative, is going to have a negative sign in front of it. And there's going to be a minus sign here in the middle simply because of Green's theorem. So then we're going to have a negative here and a negative here, and so we can factor out the negative sign. And write that this line integral is going to be equal to the double integral where we'll have, in place of this, we'll have negative dv dx plus du dy, right? That's for this line integral. So I just talked about the details. I'm going to display it shortly of what's going to happen to this line integral. Now, when we move on to this line integral, notice that v dy is like the second guy here, if you just want to think of it that way. And however, dv dx appears first here. And here we have u dy. So this should be corresponding to the v dy here. So and this line integral, what that means is the consequence of that is that instead of dv dx, we're going to have du dx, and then we're going to have minus dv dy. Yeah, so on this part, we're going to have du dx minus dv dy, and that's simply because if you pay attention here, the u is with dx here, whereas the v with the dx here, and so on. Okay, but yeah, I just talked about the detail of this, and I talked about the detail of this and how we're going to factor out a minus sign to put in front of this quantity in the parentheses, but the quantity in the parentheses will have a plus sign in the middle. Now, if I say any more, it'd be abusive, so ask questions, if you need to, but from everything I said, this needs to follow, right? This should follow. Okay, here's what's really neat, which is that we said f is analytic, meaning f is differentiable. But by definition, and I have a video dedicated to this, by definition, if f is analytic, it has to fulfill the Cauchy-Riemann conditions. And so I have a whole video dedicated to the Cauchy-Riemann conditions. And so check out that video if you want to learn more. But they're basically, the Cauchy-Riemann conditions are the requirement for differentiability for functions of a complex variable. That is, saying f of z is differentiable, that is analytic, means that the Cauchy-Riemann conditions hold. And these are the Cauchy-Riemann conditions, which is that when f of z is u plus iv, that the partials du dy and dv dx be related by this equation, and you get it. These guys also have to hold. These together are the Cauchy-Riemann conditions. But then, since we said because of f of z being analytic, the Cauchy-Riemann conditions have to hold, and these two double integrals, we have dv dx plus du dy turn into dv dx, and then minus dv dx because du dy is negative dv dx. So this here is 0. And then similarly, because du dx has to equal dv dy, du dx minus du dx is what we're going to get here. And therefore, this here is 0. So both of these double integrals are 0, and subsequently we get the desired result, what we're seeking to prove. Yeah, okay, cool. I hope you really appreciated this. And here's a summary of Cauchy's theorem. Keep watching. Take care.